Imagine a vast universe of data. Stars are data points, constellations, patterns. PyTorch is like a powerful telescope helping us explore and understand this universe. It is a machine learning library. PyTorch allows us to build artificial intelligence much like we explore the cosmos. Deep learning is a subset of machine learning. It uses artificial neural networks. These networks learn from data. PyTorch excels in this realm. It provides the tools to build these networks, train them, and use them for predictions. PyTorch is popular for a reason. It's flexible and user-friendly. Researchers and engineers use it. They push the boundaries of AI. From self-driving cars to medical diagnoses, PyTorch is there. It unlocks the secrets hidden within data. PyTorch speaks the language of Python. This makes it approachable. Python is known for its readability and ease of use. Developers find PyTorch intuitive. It feels like writing regular Python code, but with the power of deep learning behind it. One of PyTorch's strengths is its dynamic computation graph. Imagine a musical score. It guides the orchestra. In PyTorch, the computation graph defines how data flows through the neural network, but unlike a fixed score, PyTorch's graph is dynamic. It can change during runtime. This allows for flexibility and adaptability in building complex models. The dynamic nature of PyTorch provides another advantage. It allows for easier debugging. Developers can inspect the graph at any point. They can understand the flow of data. This interactive nature makes PyTorch a favorite for research and development. At the heart of PyTorch lies the tensor. Imagine a container. It holds data. Tensors are these containers. They can hold numbers, vectors, matrices, and even higher dimensional arrays. PyTorch provides a rich set of operations. We can manipulate these tensors with ease, but PyTorch is more than just tensors. TorchScript takes center stage. It allows us to convert PyTorch models into a high-performance format. This is crucial for deployment. Imagine running our models on specialized hardware. TorchScript makes it possible. The dynamic computation graph we talked about, it's another key feature. It allows us to build models on the fly. We can change their structure as needed. This is essential for tasks like natural language processing. The flexibility of the graph empowers us to handle the nuances of language. Automatic differentiation is where the magic truly happens. Training neural networks involves calculating gradients. These gradients guide the learning process. PyTorch automates this complex task. It makes training models a breeze. Section 4. Exploring New Horizons, PyTorch in Action. PyTorch's versatility is evident in its wide range of applications. Let's start with natural language processing, or NLP. Understanding and generating human language is, well, complex. PyTorch provides the tools to tackle this challenge. Sentiment analysis, machine translation, and chatbots are just the tip of the iceberg. Next, we venture into the world of reinforcement learning. Imagine an agent. It interacts with an environment and it learns through trial and error. PyTorch empowers us to build these agents. They can play games, control robots, and even optimize complex systems. Our final destination is image classification. From identifying objects in photos to powering medical diagnoses, PyTorch excels. Convolutional neural networks are the workhorse here. PyTorch provides the building blocks to create these powerful models. Section 5. We will build a multi-layer neural network with PyTorch. We've only just begun our journey. PyTorch opens up a universe of possibilities. With its intuitive interface, dynamic nature, and powerful features, it empowers us to explore the frontiers of AI. We can build intelligent systems that learn, adapt, and solve complex problems. Imagine building a full-fledged multi-layer neural network. It can recognize patterns, it can make predictions. This is the power of PyTorch. It's not just about code, it's about understanding the universe in a new light. So, dive in, explore, and discover the wonders of deep learning with PyTorch. The cosmos of knowledge awaits.
This video is a summary of topics that include Introduction to PyTorch, Understanding tensors, scalars, vectors, matrices, and tensors, tensor data types, Common PyTorch tensor operations. Seeing models as computation graphs. Automatic differentiation. Implementing multi-layer neural networks. Setting up efficient data loaders. A typical training loop. Saving and loading models. Introduction to PyTorch. Pip install Torch. I have already installed it. Make sure you install it too. Import Torch. Print torch dot underscore underscore version underscore underscore. Print torch dot CUDA dot is underscore available. In deep learning, a tensor is a multi-dimensional array used to store data. It can be thought of as a generalization of scalars 0D, vectors 1D, and matrices 2D. Tensors are the ultimate data structure for organizing and processing inputs, weights, and outputs in neural networks, allowing for efficient computation and manipulation. It's as similar to NumPy, just working as an multi-dimensional array. So let's get into how it works. Import Torch. Import NumPy as NP. Create a 0D tensor scalar from a Python integer. Tensor 0D torch.tensor1. Create a 1D tensor vector from a Python list. Tensor 1D torch.tensor1, 2, 3. Create a 2D tensor from a nested Python list. Tensor 2D torch.tensor1, 2, 3, 4. Create a 3D tensor from a nested Python list. Tensor 3D underscore 1 torch.tensor1, 2, 3, 4, 5, 6, 7, 8. Create a 3D tensor from NumPy array. Array 3D np.array 1, 2, 3, 4, 5, 6, 7, 8. Tensor 3D underscore 2 torch.tensor array 3D copies NumPy array. Tensor 3D underscore 3 torch dot from underscore NumPy array 3D shares memory with NumPy array. Array 3D 0, 0, 0, 999. Print tensor 3D underscore 2 remains unchanged. Print tensor 3D underscore 3 changes because of memory sharing. Tensor data types. Tensor 1D torch.tensor 1, 2, 3. Print tensor 1D dot type. Float vec torch.tensor 1.0, 2.0, 3.0. Print float vec dot d type. Float vec tensor 1D dot to torch dot float 32. Print float vec dot d type. Common PyTorch tensor operations. Tensor 2D torch.tensor 1, 2, 3, 4, 5, 6. Tensor 2D. Tensor 2D dot shape. Tensor 2D dot reshape 3, 2. Tensor 2D dot view 3, 2. Tensor 2D dot t. Tensor 2D dot matmul tensor 2D dot t. Tensor 2D at tensor 2D dot t. Seeing models as computation graphs. Import torch.nn.functional as f. ytorch.tensor1.0 true label. x1 torch.tensor1.1 input feature. w1 torch.tensor2.2 weight parameter. b torch.tensor0.0 bias unit. zx1w1b net input. A torch.sigmoid z activation output. Loss f.binary underscore cross underscore entropy ay. Print loss. Now picture this. Look at the workflow diagram. Now let's deep dive into automatic differentiation. Automatic differentiation exploits the fact that every computer calculation, no matter how complicated, executes a sequence of elementary arithmetic operations: addition, subtraction, multiplication, division, etc., and elementary functions xp, log, sin, cos, etc. By applying the chain rule repeatedly to these operations, partial derivatives of arbitrary order can be computed automatically, accurately to working precision, and using at most a small constant factor of more arithmetic operations than the original program. Import torch.nn.functional as f. From torch.autograd import grad. Y torch.tensor1.0. X1 torch.tensor1.1. W1 torch.tensor2.2 requires underscore grad true. B torch.tensor0.0 requires underscore grad true. ZX1W1B. A torch.sigmoid z. Os f.binary underscore cross underscore entropy a y. Grad underscore L underscore W1 grad loss W1 retain underscore graph true. Grad underscore L underscore B grad loss B retain underscore graph true. Print grad underscore L underscore W1. Print grad underscore L underscore B. Os dot backward. Print W1 dot grad. Print B dot grad. Implementing multi-layer neural networks. Class neural network torch.nn.module. Def underscore underscore init underscore underscore self. Num underscore inputs. Num underscore outputs. Super dot underscore underscore init underscore underscore. Self dot layers torch.nn dot sequential. First hidden layer. Torch.nn dot linear num underscore inputs 30. Torch.nn dot relu. Second hidden layer. Torch.nn dot linear 30 20. Torch.nn dot relu. Output layer. Torch.nn dot linear 20 num underscore outputs. Def forward self x. Logits self dot layers x. Return logits. Model neural network 53. Print model. Num underscore params sum p dot numal for p in model dot parameters if p dot requires underscore grad. Print total number of trainable model parameters num underscore params. Print model dot layers 0 dot weight. Torch dot manual underscore seed 123. Model neural network 53. Print model dot layers 0 dot weight. Torch dot manual underscore seed 123. Model neural network 53. Print model dot layers 0 dot weight. Print model dot layers 0 dot weight dot shape. Torch dot manual underscore seed 123. X torch dot rand 150. Out model x. Print out. With torch dot no underscore grad. Out model x. Print out. With torch dot no underscore grad. Out torch dot softmax model x dim 1. Print out. Setting up efficient data loaders. X underscore train torch dot tensor. -1.2, 3.1. -0.9, 2.9. -0.5, 2.6. 2.3, -1.1. 2.7, -1.5. Y underscore train torch dot tensor 0, 0, 0, 1, 1. X underscore test torch dot tensor. -0.8, 2.8. 2.6, -1.6. Y underscore test torch dot tensor 0, 1. From torch.utils.data import dataset. Class toy dataset. Def underscore underscore init underscore underscore self xy. Self.features x. Self.labels y. Def underscore underscore getim underscore underscore self index. 1 underscore x self.features index. 1 underscore y self.labels index. Return 1 underscore x, 1 underscore y. Def underscore underscore len underscore underscore self. Return self.labels.shape 0. Train underscore ds toy dataset x underscore train, y underscore train. test underscore ds toy dataset x underscore test y underscore test. Len train underscore ds. From torch.utils.data import data loader. Torch.manual underscore seed 123. Train underscore loader data loader. Dataset train underscore ds. Batch underscore size 2. Shuffle true. Num underscore workers 0. Test underscore ds toy dataset x underscore test y underscore test. Test underscore loader data loader. Dataset test underscore ds. Batch underscore size 2. Shuffle false. Num underscore workers 0. For IDX, X, Y in enumerate train underscore loader. Print F batch IDX1, XY, train underscore loader data loader. Dataset train underscore DS. Batch underscore size 2. Shuffle true. Num underscore workers 0. Drop underscore last true. For IDX, X, Y in enumerate train underscore loader. Print F batch IDX1, XY. We have all reached the end of our first multilayer neural network using PyTorch. The last climax is the training of your network. Import torch.nn.functional as f. Torch.manual underscore seed 123. Model neural network num underscore inputs 2, num underscore outputs 2. Optimizer torch.optim.sgd model.parameters lr0.5. Num underscore epochs 3. For epoch, in range num underscore epochs. Model.train. For batch underscore IDX, features, labels and enumerate train underscore loader. Logits model features. Loss f.cross underscore entropy logits, labels loss function. Optimizer.0 underscore grad. Loss dot backward. Optimizer.step. Logging. Print f epoch 103d num underscore epochs 03d. F batch underscore idx 03d len train underscore loader 03d. F train val loss colon dot 2f. Model.eval. Optional model evaluation. Model.eval. With torch.no underscore grad. Outputs model x underscore train. Print outputs. Torch.set underscore print options psi underscore mode false. Probus torch.softmax outputs dim1. Print probus. Predictions torch.argmax probus dim1. Print predictions. Predictions torch.argmax outputs dim1. Print predictions. Predictions y underscore train. Torch.sum predictions y underscore train. Def compute underscore accuracy model data loader. Model.eval. Correct 0.0. Total underscore examples 0. For IDX, features, labels and enumerate data loader. With torch.no underscore grad. Logits model features. Predictions torch.argmax logits, dim1. Compare labels predictions. Correct torch.sum compare. Total underscore examples len compare. Return correct total underscore examples item. Compute underscore accuracy model, train underscore loader. Compute underscore accuracy model, test underscore loader. Saving and loading models. It's the final step in our model. Torch.save model.state underscore dict model.pt. Model neural network 2 needs to match the original model exactly. Model.load underscore state underscore dict torch.load model.p8 waits underscore only true. Once it's done, you will find the model path on your notebook. Feel free to download and explore on your own. It will be around a 6 GB file. That's your deep learning model you just trained.
Am I the only one that didn't know PyTorch could be this amazing? Let's wrap it up, folks. I hope you found this video helpful and that you're feeling a bit more confident about using PyTorch for your projects. If you enjoyed this video and want to see more content like this, don't forget to hit that like button and subscribe to the channel. Also, let me know in the comments what PyTorch topics you'd like us to cover next, or if you have any questions. I'd love to hear from you. Your feedback helps us create content that's tailored to what you're interested in. Thanks for watching, and until next time, keep coding and stay curious.